Another important characteristic of water is that it can both donate and accept a proton, that is an H+. And the name this is given is amphoteric. Amphoteric means the ability to either donate or accept an H+. And it's a remarkable feature of water. So let's write out our reaction. We have H2O in the liquid phase reacting with another water molecule in the liquid phase and forming H3O plus in the aqueous phase plus OH minus in the aqueous phase. So H3O plus is a hydronium ion, OH minus is the other partner in this reaction, and this is an equilibrium, and we know exactly how to write that equilibrium constant. We can write this as the product of the concentrations of the products divided by the concentration of the reactants, except that we notice something very interesting, and that is we have pure water on the left-hand side and H3O plus and OH minus on the right-hand side. And when that equilibrium is established, we know when we write the equilibrium constant that all pure liquids and pure solids drop out. So that's the expression for the equilibrium constant. It's the product of H3O plus times OH minus, and at 298, that's equal to 1 times 10 to the minus 14 at 298 Kelvin. Okay, but look what this says. It says something very important. It says that one water molecule is donating an H+, and the other is accepting an H+. And therein lies the characteristic of water making it amphoteric, the ability to either donate or accept H+. Well, we know that this is going to be related to a Gibbs free energy surface, but let's explore something. Let's take a perspective that assumes that we're looking at the forward reaction. So we have H2O liquid reacting with H2O liquid, forming in an equilibrium reaction our OH minus, which is in the aqueous phase, plus our H3O plus, also in the aqueous phase. Now, with an equilibrium constant equal to 1 times 10 to the minus 14, when we express this in terms of the free energy, we know that our equilibrium constant is now 1 times 10 to the minus 14, but we know that we can calculate the change in Gibbs free energy for this reaction. That's equal to minus RT times log of K equilibrium, but we're looking at this expression for the particular case of water reacting with itself to form H3O plus and OH minus, and so this is minus RT times the natural log of the equilibrium constant for that reaction between water and itself to form H3O plus and OH minus. And when we do that calculation, that gives us a change in Gibbs free energy for the reaction, 79.9 kilojoules for the reaction as written. But now let's take a contrasting perspective from this first perspective. Let's look at the world from the opposite direction. We'll call this our second perspective. And we know that our Kw is 10 to the minus 14. But now let's write the reaction the other way around. Let's write H3O plus in the aqueous phase plus OH minus also in the aqueous phase, going to the products H2O liquid plus the other product H2O. This forms an equilibrium just as well. But we also know that when we reverse the direction of a reaction, we have to invert the value of the equilibrium constant. So now we have a new equilibrium constant. We'll call that Kw prime, and we know that that has to be 1 over the equilibrium constant for the reverse reaction. And so we know that this is equal to 1 times 10 to the plus 14, at 298. Well, that's a very large equilibrium constant. That means that the reaction is shifted almost completely to the right, almost completely converting all reactants to products. But we can calculate the change in Gibbs free energy. That's equal to minus RT times the log now of Kw prime. And when we do that calculation, we have a change in Gibbs free energy for the reaction of minus 79.9 kilojoules. That is a very large negative free energy change in that reaction. So let's track this then. Let's look at the reaction in that forward direction. And we know how to calculate delta G is equal to minus RT log Kw, which is equal to plus 79.9 kilojoules. That means that the products, H3O plus and OH minus, lie at a much higher Gibbs free energy than does H2O reacting with itself. But the important thing here is that while this reaction is spontaneous as it moves downhill from H3O plus OH minus to water, it reaches an equilibrium that is very far to the left, that is almost entirely shifted toward H2O itself. But the difference between that equilibrium point and pure H2O is profoundly important, because it turns out that that reaction, the equilibrium position, has a huge impact on any acid-base process that we look at. And to see that, let's turn this around and look at the reverse reaction. Let's look at the reaction now of H3O plus aqueous plus the hydroxide anion, also aqueous, forming water in the liquid phase. And in this case, when we calculate delta G, we're going to have exactly the same magnitude, but because we've reversed the direction, now we have a spontaneous reaction converting H3O plus and OH minus to water, and that reaction releases free energy until it reaches the equilibrium position. But that equilibrium position is shifted all the way to the right, almost all the way, because delta G under standard conditions in this case is equal to minus 79.9 kilojoules. It's this reaction that on the face of it looks like a reaction that's not terribly important because it's shifted so far toward pure water. But it's very important for all acid-base reactions, because this reaction H3O plus OH minus means that if I put an excess of H3O plus into a solution, that reaction between the H3O plus and the OH minus will move very quickly toward the formation of H2O liquid. And it turns out that understanding the degree to which that change in free energy drives that reaction toward water is an incredibly important process in acid-base reactions. And it's called the neutralization reaction because it effectively neutralizes the H3O plus and OH minus, forming water.